From 5G networks to aerospace systems, from artificial intelligence to quantum technologies, from behind the scenes of innovations to real-world applications. Welcome to Innovations Unplugged, the Rohde Schwarz Technology Podcast.
2025 has been given a title. UNESCO declared it the International Year of Quantum Science and Technology. So let's join the global stage with today's episode. Hello, I'm Markus Haller.
And I'm Inga Müller-Sientop, and we are your hosts today. Quantum technology is as fascinating as it is transformative. No longer confined to labs or lectures, it's already part of our daily lives. And yet we're only scratching the surface of its potential. To really grasp the scale of it all and how Rohde Schwarz fits into the picture, we've invited an expert to join us.
Claudius Rieck holds a PhD in time domain quantum electrodynamics, and he is fascinated by how fundamental science can shape future products. He is a colleague from Zurich Instruments, a proud member of the Rohde Schwarz family that enables research and industry to build quantum technology and especially quantum computers. Welcome, Claudius.
Thanks a lot for having me.
So, Claudius, let's start with the basics. Quantum computing may be grabbing headlines, but it's just one aspect of quantum technology. Can you briefly give us an overview?
Absolutely, very happy to do so. So quantum technologies are all technologies based on quantum phenomena, phenomena based on quantum science. And there are typically three pillars we name, which is quantum computing, so calculating with quantum so-called qubits, quantum communication, so using quantum phenomena to secure communication channels, and quantum metrology, which is everything where we measure with quantum systems. And this also includes, for example, quantum sensing, where we use a quantum system to sense, for example, magnetic field strength or also gravitational field strengths.
Okay. So based on that, quantum technology actually already is a part of our lives, often without us even noticing. So can you give us some real-world examples where quantum physics, quantum phenomena, quantum science is at work behind the scenes already?
I mean, we are celebrating 100 years now, so this means a lot of the technology developed in the last century already is based on quantum technology. One of the most famous one is lasers in the end. They are basis for manufacturing, so cutting with lasers, but also communicating via glass fibers around the entire globe, which enabled, for example, the World Wide Web, the internet, how we know it today. So lasers is the first one. The second one would be for medical diagnostics, magnetic resonance imaging, where we can look into soft tissues, where we can identify different tissues. Also, this is based on a quantum effect, observing a quantum effect in the end. And the last one, which I would like to highlight, are atomic clocks. I'm pretty sure most of our listeners did not hear about that and where they used, but they are one of the key elements for global positioning systems like GPS, GLONASS, etc., because they allow us to navigate with our cars, or also even if we go for a run in the morning with our fitness watches, which many use for tracking their run in the morning.
I think you're right that not so many people know the background of it, but we all use it. So can you explain what an atomic clock is and what it does?
More than happy to do so. And I think everybody knows a clock. Yeah. So
yes.
the most mechanical one, you take a pendulum, and this gives you a certain frequency. An atomic clock does basically do the same thing, but instead of a mechanical pendulum, as we might know it from the wall clock in our grandparents' apartment, we use atoms and individual atomic resonances, which are specific to an atom and which are universal. So no matter where we have such an atom and such a then so-called clock transition, which we drive on a satellite or somewhere on the Earth, it's always the same. And therefore, we can have distant clocks which are perfectly synchronized. And so we can measure the distance between those clocks or the position where we are with our car or on our morning run.
Actually fascinating to hear that I'm using quantum technology on my smartphone. And just a little story from my side. Recently, I've broken my ankle and I needed an MRI. And it's interesting to see how it actually functions. So quantum technology really helped me out here.
We're using technologies today that are based or only possible because of given quantum phenomena. But the real buzz around quantum today is about what's next. So it's called the second quantum revolution. Can you explain?
When we talk about the second quantum revolution, obviously there has to be a first quantum revolution. And these were the technologies we just discussed. Yeah, lasers, MRIs, atomic clocks, but there are much more. The first quantum revolution was mainly about observing quantum effects and use them, for example, to do the imaging on your ankle, Markus. While the second quantum revolution now focuses on manipulating quantum systems one by one, initiating and controlling them. And this is the big difference between the first and the second quantum revolution. In the first, we mainly observed. And in the second quantum revolution now, we really start interacting with the quantum world kind of on purpose.
So we've seen first generation quantum technology is already impressive, but this is not the end. With this shift from using given quantum effects and understanding them to actually controlling quantum systems. So this opens up incredible possibilities. So let's take a closer look on quantum computing and go back to the basics again. Claudius, what is a quantum computer and why do we need one?
Quantum computers are computers which calculate with so-called quantum bits, which are in short called qubits. In analogy to a classical computer where we have bits, which is either a 0 or 1, state of 0 and 1, qubits take all values in between 0 and 1, but also so-called superposition of those values. And then using another quantum phenomenon called entanglement. And the challenge you really have is you want to use superposition and entanglement to perform computing, to perform algorithms where one qubit will react on the action you do to another qubit. Unfortunately, both entanglement and superposition can be fairly easily destroyed by interaction with the surrounding. Okay. And this is the reason why it is often very important to control the surrounding very well, or to have qubits which are more isolated from the outside world. Okay. And one example is for superconducting qubits and for semiconducting spin qubits. This is why they are put in a refrigerator to have no impact from so-called thermal occupation. And this is one of the main challenges we have. In one way, we want to interact with the qubits. So we need this interaction. Yeah. But if we want that they perform an algorithm, we want them to have them isolated from the surrounding as good as possible. That's one of the biggest challenges.
Fascinating, but of course we are still in early stages. Claudius, can you tell us a bit What's being researched right now in quantum computing research labs all over the world?
So quantum computing research labs are working on the building blocks of quantum computers. So first of all, they design individual qubits. There's a variety of different qubits. There are superconducting qubits. There are so-called neutral atoms, ions, nitrogen vacancies. This is one building block. The other part is putting them next to each other and allow qubits to interact and address them individually. And of course, and this is where also we can then into the game, is to control those registers of qubits and read them out.
Can you elaborate a bit on this, controlling qubits?
Yes, it depends strongly on the kind of qubits. So some technologies you address optically, for example, with lasers. Some you address electronically. So, for example, with microwave signals. What we are doing, providing electrical signals. And these are kind of among the most precise signals you can generate today. And we don't need them once. We need them in scale, hundreds and millions of times. And this is one of the big challenges we are actually facing.
How far are we in the research process?
I think this is one of the most challenging questions which comes up always if we talk about this topic, because everybody wants to understand, okay, when can we have a real quantum computer which solves everyday problems? The main question is, what do we take as a measure for progress in the lab? And this is, I think we can take the number of qubits. So if you think about a powerful quantum computer, we would talk about something like 100 to 1,000 logical qubits. So what is very important to know, that one logical qubit consists of multiple physical qubits, so the real qubits which you can see or you can observe physically in the lab. And you need roughly 100, as a ballpark number, 100 physical qubits to have one logical qubit. So this is kind of the state of the art where we are at the moment. So there is a long way to get to real world and everyday application.
A lot of our audience know how a quantum computer roughly looks like, but they may imagine this shiny, huge thing with a lot of cables on. But how does a test measurement setup look like? What do we imagine? Like, there must be some test measurement instrument, there must be cables to where, from where?
Give us the lab tour.
If you enter a lab, especially on superconducting, for superconducting qubits, the first thing which you will see is this cryostat, which you described, typically 3 meters high. It's a bigger rack, and if it's closed and the qubits can sit at kind of in their comfortable 10 millikelvin regime, then you see only a white tube, first of all.
Like a really big refrigerator, right?
Exactly. It's a very big, very powerful refrigerator, which achieves very, very low temperatures, so close to absolute zero. It's even colder than outer space. So next to the refrigerator, we have racks full of electronic boxes in the end. They look fairly boring, I must say. They have front panel, they have many connectors. There's no display because you control them remotely with a classical computer. And you can say roughly you need something like 2 to 3 lines per qubit. Okay. One for control, one for readout, and then potentially another one, for example, for a coupler. So this, you can imagine, for a 100 qubit chip, this means roughly 300 cables.
Okay.
And if you maybe look at your computer,
yeah.
So typically we connect one cable for the power towards the docking station, etc.
And that's it.
And that's it. Also, the analogy to classical computing in kind of the early steps is a very good comparison. If you think about how computers look, for example, if you go to the Deutsche Museum close by, you can see those huge first computers.
Yes.
They also filled an entire room.
Yes.
And they were barely able to calculate up to 1 million. Yeah?
But everyone was already excited about it. What may be possible?
It was super exciting because before you had to do all the calculations with pen and paper.
Yes.
And if you did a mistake, then you had to start all over again. So, I think we are at the similar stage at the moment with quantum computers.
Okay.
The technology fills an entire room, and the capabilities are not very impactful on our everyday life yet. But we need to go a similar trajectory to classical computers. So we need to improve the qubits. We need to scale the number of qubits significantly. And therefore, we need to miniaturize also the entire enabling technology, which means, for example, getting rid of the cables, shrinking the control electronics. And it becomes even more severe if you think about the numbers we discussed before. We talked about 100,000 or even 1 million physical qubits. So this would mean millions of cables. I don't want to be the PhD student connecting those because you don't do anything else for 5 years. So this is exactly where we need to innovate much more and where we need to find solutions.
Claudius, from your point of view, how do you think Zurich Instruments will drive this? What role do you think will Zurich Instruments play in this field?
We have the mission to help build a meaningful quantum computer which solves real-world problems. This means we need to go the next steps from the few tens to hundreds of qubits, physical qubits we have in the labs at the moment, all the way to having 10,000, hundreds of thousands of qubits there. And for the enabling technologies, we have to support this trajectory and we have to innovate in the same way, integrating our technologies and also coming up with innovations which allow, for example, to put so many cables into one cryostat, bring the signals down to qubits in the end.
Exciting challenge, being ahead or thinking ahead of what is needed. Is that right?
Yes, absolutely. In the end, it's a co-development with the companies working on the qubit chips, working on quantum computers, and we are enabling in the end their progress. We are only able to do that together, because there are so many individual problems to solve.
What makes Zurich Instruments the right partner here?
First of all, I want to name the people. Many of the colleagues come from cutting-edge research labs. They were some of the first who were researching on this kind of phenomena. But in addition, we have also many electrical engineers and also software engineers which came from leading companies in those fields before. And I think this mixture where we bring in the application knowledge from one side and also the knowledge how to manufacture, how to engineer solutions and enable the next steps in the research and also the implementation of quantum computers is absolutely crucial. And there is also the big advantage which we have as part of the Rohde Schwarz group. Here we have knowledge since almost 100 years on how to generate electrical signals, especially in the microwave domain, with very high precision, but also having this ability to put it in very reliable systems and having the background on how to scale this onto industrial level, which is exactly what the quantum industry needs to mature in the next years.
To wrap up today's episode about all things quantum computing, I do have a question out of curiosity for you personally. What excites you most about that field of technology?
I think it's one of those fields where fundamental research and application is super close together. And the part which is exciting to me is that many of the answers we will need to scale quantum computing and make it impactful for everyday problems is being researched at the moment. And for me, this is exactly the passion to bring cutting-edge research into products and make an impact for as many people as possible.
Thank you for your time, Claudius. I very much enjoyed this conversation, and it's really, really fascinating to learn more about these technologies.
Yes, thanks a lot, Claudius, for sharing all this and also your excitement about quantum.
And if you as audience, if you as listeners are still here and want to learn even more, dive deep into the topics of Zurich Instrument, check out their website, check out the latest issue of Rohde Schwarz News, our magazine. We covered quantum technologies in depth. All links are in the show notes.